Welcome to qnawire.
Hi everyone, so what we have is a turbocharger system that is connected to a charged air cooler to cool the air coming into an IC engine. What we're asked to find is the temperature at the outlet of the compressor and the minimum volume flow rate of air required to avoid knocking. So the first thing we're going to do is just go ahead and do the energy balance relation for our turbine. So we know that this is going to be equal to m dot h1, which is equal to m dot h2 plus the work that is pulled out. And since the compressor and turbine are directly connected to each other, we know that this work that's extracted from the turbine is directly transmitted into the compressor. So what we can do is we can solve for a work, which gives us a power equal to m dot h1 minus h2. And by plugging in for these values, we see that the work is equal to 1.06 kilowatts. Next, what we can do is we can write the energy relation for our compressor, and therefore we can calculate the temperature that leaves the compressor at the end. So what we can do is say that the energy relation for the compressor will be m dot h1 plus w dot is equal to m dot h2. Now we can go ahead and rearrange terms and set these equal to 0, and therefore we see that m dot cp t1 minus t2 plus w dot is equal to 0, and we just use the definition that h is equal to cp times t. So solving this expression for t2 gives us that t2 is equal to t1 plus the work over m dot cp, and by plugging in for these quantities, T1 is 323 Kelvin. Our work, which we solved for before, was 1.06 kilowatts, all over our m dot, which is 0.018 kilograms per second, times our CP of 1.005, gives us a temperature at the outlet of the compressor equal to 382 Kelvin, which is equal to 109 degrees Celsius. Next, what we can do is we need to find the volume flow rate that is required to prevent knocking. So what we can do now is we can say that the m dot of the comp times Cp times 109 minus 80 is equal to m dot Cp 40 minus 30. And therefore what we can do is we can go ahead and solve for the volume flow rate. We can say that the volume flow rate is going to be equal to m dot all over rho. And this is equal to 29 times m dot CO comp all over 10 times rho. And now what we can do is we can use the ideal gas law to plug in for rho and say that this is equal to 29 m dot, I'm just going to call that C for now, RT over 10p. And by plugging in for these quantities, we can see that our V dot will be equal to 29 times our m dot, which is 0.01 kg per second, times R, which is 287 joules per kilogram Kelvin, times our temperature, which is 303 Kelvin, all over our density, all over our pressure, which is 10 times 130 times 10 to the third Pascal. And this gives us a volume flow rate equal to 0.0349 cubic meters per second. And that's our final answer.